All right, so the first thing that I would like to talk about today is instantaneous power in multi-frequency circuits. Or actually, let's call it instantaneous and average power. In multi-frequency circuits. And in some ways, this is going to be very similar to what we talked about on Friday with regards to circuits that are excited at a single frequency. However, we're going to see rather quickly that the math gets pretty darn gross, pretty darn fast. And that is going to give us a good segue into why the use of effective values is such an important topic in the field of electrical engineering, which is our second topic for today. Okay. So starting things off pretty similar to what we did last Friday, let's say that I have some time varying source. Again, it's completely unimportant as to whether or not it is a current source or a voltage source, but this source is providing multi-frequency excitation. Here we have our simple linear black box network. And the voltage drop across our network will be designated as V of t, and the current flowing into our network will be designated as I of t. And notice that the current is flowing into the positive polarity terminal like we had last Friday, such that we're calculating the absorbed power. Okay. So this time, let's say that our voltage V of t is going to be composed of two different sinusoids oscillating at different frequencies. I'm going to limit our look at this phenomenon to two excitation frequencies because as you'll see, the math gets real terrifying real fast, and anything beyond this would just be utterly overwhelming. And this isn't going to be far from that to begin with, okay? So let's say that I have our first voltage signal, Vm1 cosine omega 1t plus some phase angle theta v1. And now I have my second signal, Vm2 cosine omega 2t plus theta v2, like so. And I'm going to call this part right here essentially v1 of t. And this part right here will be v2 of t. Similarly, I'll have a time varying current, I of t, of the form Im1 cosine omega 1t plus theta I1 plus Im2 cosine omega 2t plus theta I2. And we'll decompose this into two parts as well, where we have I1 of t and I2 of t. So our instantaneous power in this system, P as a function of time, is just going to be the product of our current and our voltage, like we saw last Friday. But now we're going to have essentially four different terms, okay? So we'll have V1 times I1 plus V2 times I1 plus V1 times I2 plus V2 times I2. And now I'm going to suffer through expanding all of this out, okay? So the V1 times I1 term is literally identical to what we did on Friday. So that's going to look like a factor of 1/2 VM1 times IM1 times the cosine of theta V1 minus theta I1 plus 1/2 VM1 IM1 cosine of twice omega t plus theta V1 plus theta I1. And now I'm going to add to that our other terms. So just to make sure we're all on the same page as to where the heck these things are coming from, I'm going to reintroduce you to that trig identity, where we would have cosine of some angle 1 times cosine of some angle 2 is simply the cosine of angle 1, excuse me, let's do, I forgot to factor 1/2 as well, excuse me. Brain is elsewhere. Cosine angle 1 minus angle 2 plus 1/2 cosine of angle 1 plus angle 2. All right. So when I multiply V2 times I1, I'm going to wind up with 1/2 VM2 times IM1. And now I'm going to have cosine of the difference of the angles, okay? So I've got omega 2t plus theta V2 minus the quantity omega 1t plus theta I1. So I'm going to lump those frequencies together, and this is going to look like omega 2 minus omega 1 t, and then I'll have theta V2 minus theta I1. So one thing that we can see here really quickly is that when we have these cross frequency terms, it's going to give us two sinusoidally oscillating terms instead of a DC term and a sinusoidally oscillating term. Okay. Now, applying the second part of that trig identity, I'm going to have 1/2 VM2 IM1 cosine omega 2 plus omega 1 t plus theta V2 plus theta I1, like so. And continuing on, now I'm going to do the V1 times I2 term. So this is going to look like 1/2 VM1 IM2 cosine omega 1 minus omega 2 t plus theta V1 minus theta I2 plus 1/2 VM1 IM2 cosine omega 1 plus omega 2 times time plus theta V1 plus theta I2. And then lastly, I'm doing my V2 times I2 term. So these two are at the same frequency, so it's going to look incredibly similar to what we had when we did V1 times I1. So that'll look like 1/2 VM2 IM2 cosine theta V2 minus theta I2 plus 1/2 VM2 IM2 cosine twice omega t plus theta V2 plus theta I2. So we've got 8 terms here, but this can be simplified a little bit, okay? So let's think about things here really quickly, okay? So I'm going to underline all of my DC terms really quickly. So let's do those in red, okay? So everything in red is going to be DC. So this is a DC term right here. And this is a DC term right here. Okay? I'm going to put a little note DC and DC. Okay. How many of you, hopefully most of you, are aware of the trig identity that cosine of negative x is the same thing as cosine positive x? Practically all of you, right? Well, the reason why I'm bringing that to your attention is because we have two terms, one where we have cosine of omega 2 minus omega 1t, and we have another term where it's omega 1 minus omega 2. Well, omega 1 minus omega 2 is just negative omega 2 minus omega 1. So those two terms are actually at the exact same frequency. So I'm going to underline those guys in maybe this light blue like this. So this guy is at a frequency of omega 2 minus omega 1. And this guy right here is also at a frequency of omega 2 minus omega 1, if we understand that trig identity that cosine x and cosine negative x are the same thing. A little bit easier to see are these terms right here. So this is a term that's going to be having a frequency of omega 1 plus omega 2. And this guy right here is also at that same frequency of omega 2 plus omega 1. Okay. Now we've got this guy right here, which is at a frequency of twice omega 1. Sorry, I neglected to put an omega 1 right there, and it looks like I forgot to put an omega 2 right there. Sorry about that. And then let's do this guy in this green color right here. This term is oscillating at a frequency of twice omega 2. So essentially, if we have two different frequencies of excitation, our power winds up with 5 different frequencies. DC, the difference of the frequencies, the sum of the frequencies, twice frequency 1 and twice frequency 2. So it winds up being, how it works out is it's 2n plus 1 is the number of total frequencies we'll see, where n is the number of excitation frequencies. So obviously, it's just going to get more and more horrifying as we continue to add higher order terms and all of that kind of good stuff in here. Okay. So one thing that I want us to observe from this horrifying mess here is that the DC terms are still going to represent our average power, okay? So on average, all of those sinusoidally oscillating terms, so our non-DC terms, they have an average value of 0 because they are simply sinusoidally excited signals, right? So it doesn't matter what frequency they're at, if they're sinusoidally excited, on average, they look like nothing, okay? So from this thing, we could actually see that our average power is just the terms 1/2 Vm1, Im1, cosine theta V1 minus theta I1 plus 1/2 Vm2, Im2, cosine theta V2 minus theta I2. What's really interesting about this particular expression to me is that essentially it looks like we were computing average power using superposition, okay? Meaning that we're just treating what's going on at our first frequency, calculating the power, treating what's going on at our second frequency, calculating the average power, and then adding those two things up. Why that's very interesting to me as a huge math nerd and all of that kind of stuff is that superposition is a linear property, but power isn't, because power is dependent on the square of signals and things like that, okay? So this actually kind of breaks our perception of what superposition can do, and it's because of all of those cross-frequency terms effectively canceling each other out. Okay. So it would be useful to us if we could potentially calculate our average power or something like that in a system like this without having to go through this horrifying amount of legwork. And so that's going to bring us to our discussion of effective values for periodic waveforms. Okay. So how do I put this? In your homeworks, exams, etc., I don't think I'm ever going to actually make you use this instantaneous power relationship because it is so ridiculously unwieldy, and it doesn't really give us a lot of useful information. It gives us a ton of information, but whether or not it's useful is an entirely different bag of cats, okay? So realistically, I'm more interested in you guys picking up this relationship out of everything that we've just derived. And once we understand effective values in a multi-frequency system, which isn't going to be that big of a stretch, you actually have a different way to wind up computing this anyway. Okay. All right. So let's talk about effective values. So for those of you that had me for Engineering 221, at least for the next 10 minutes or so, this is largely going to be a review. Okay. Effective values are something that we have all been dealing with, whether we realize it or not, for most of our lives. So how I typically frame this discussion is I attempt to draw a very shitty picture of a receptacle in a room like we have here. And so I'll do that same thing here. So let's say that I have a receptacle that looks something akin to this, right? So I'm going to have I think it's usually the long blade here on the left, the shorter blade here on the right for a polarized plug, and then this kind of half moon thing here, where this particular terminal corresponds to our ground wire in our wall. This guy right here corresponds to our neutral wire. And this guy over here corresponds to our hot wire. in a single phase AC system, like most homes, commercial residences, and all that kind of stuff. Kyle, what's up?
Why? How much is it?
So for so older construction may not actually have the ground wire, the place on the receptacle for you to plug it in. Also, older receptacles may not have the blades where you plug things in of different sizes. You might just see two small ones. So for what it's worth, you look at the plug on my laptop charger. Both of these blades are literally the exact same size, which means it doesn't matter how I plug this in. The reason for that you'll learn in your electronics classes, but effectively the AC that comes in through this plug goes into this brick right here, which has what's called a rectifier. It has a full wave rectifier inside of it, which is converting both the positive portion and the negative portion of the AC signal into a DC voltage, which is then supplied to the actual computer and all of that kind of stuff. This guy does not have a ground pin at all because it isn't needed for this particular piece of equipment. For other things that are going to handle significantly larger currents, they probably do have ground pins, and they also have different size blades on their plug to polarize things and connect it correctly. We aren't required to ground everything. It's usually for safety purposes, and talking about ground requirements could literally be an entire course of its own. Usually your ground wire and your neutral wire wind up tied together outside of your home in your literally like your lightning rod or ground spike. It's literally a piece of metal that's driven into the ground to give your home access to a true earth neutral or a true earth ground, and you tie your neutral to that in most forms of construction. Got a little away from us, but that's okay. For what it's worth, your neutral wire and your hot wire are not usually red and black in a single phase AC system like you might see in your homes. It's typically white and black because those are the two colors that come inside of your Romex packaging. Usually, I believe the white is the neutral and the black is the hot wire. So if we were to pull the cover off of that guy and pull that outlet out, we'd very likely see a black wire, a white wire, and potentially a green wire that's tied to the ground lug on that particular receptacle if it's wired correctly, but this building is old, so who knows? Not to throw shade, but when we got the power lab down here wired for three-phase, I actually had to go back through and rewire it myself because the guys that did it weren't paying attention to make sure that all of the phase conductors were oriented correctly. And so some of our motors were spinning backwards, and I did not want that to happen because it could confuse students. So I literally got my multimeter and all that kind of stuff and rewired that room myself. Me and Dr. Batari spent an afternoon doing it. But anyway, so. Okay, back to what we're actually supposed to be talking about here. So let me ask somebody who didn't take me for 120. Will, what's the voltage that's provided by an outlet like this? 120. So you're both right and wrong for the same reason that Nikolai was right and wrong, if I'm remembering correctly, last quarter. So the 120 that we've all been told that our outlets provide is actually the effective value for the voltage that is being supplied. So realistically, because we are dealing with an AC system, we should see that we have some time varying voltage, and that time varying voltage, V of t, for what it's worth, should be close to, but it won't be exactly. So let me just put approximately here. I believe it's 169.7 cosine 120 pi t plus some generic phase angle theta v that depends on when we start actually looking at our signal. This has an effective value of 120 volts RMS. Okay? So let's talk about what that effective value actually means here. Okay. So an effective value for a periodic signal is a DC representation of that signal So a DC representation of the periodic signal that delivers an identical or equivalent amount of average power. So essentially, if I were to connect, let's say, some sort of very simple resistive load like a light bulb or a lamp or something like that, to an outlet here in this room, and we used a device called a watt meter to measure the amount of average power that was absorbed by that lamp, it would absorb the exact same amount of power plugged into the wall as it would if we had access to a 120 volt DC source. That's where the equivalency comes in for these effective values. So we can use that relationship to derive a mathematical expression for effective values for any type of periodic signal that we might be interested in. Okay, so let's say, so let's do it for voltage, and it's going to wind up coming out as the exact same relationship for current. But anyway, so let's say that I have a DC system, okay? And I'm dealing with a resistive load specifically because we're only talking about average power here. And we know that capacitors don't absorb any average power and inductors don't absorb any average power. So we can limit our scope to resistors without actually messing anything up, since they're the only things that are going to absorb average power to begin with, right? So in a DC circuit, we know that the power absorbed by a resistor in terms of the voltage could be written as simply our DC voltage squared divided by the resistor value. And that D looks too much like a P for my taste, so I'm redrawing it. Okay. Well, in an AC system, and actually instead of calling this PDC, I'm going to call it average power, because the average power in a DC system is the same thing as the instantaneous power. It's the only power because it's a fixed value, okay? So in an AC system, we know that we have that relationship 1/2 Vm Im cosine theta V minus theta I. Well, for a resistor, cosine theta V minus theta I is just 1 because the phase angle of the current and the phase angle of the voltage are the same thing. So we would have 1/2 Vm Im. And we know that Im is just Vm divided by R. So that would look like 1/2. Now I'm going to fancy this math up a little bit here. Actually, let's not do that. Let's do it a different way. So let's say instead, let me take a side note here. I don't want to constrain us to just single phase AC circuits or something like that, okay? So this is just a side note really quickly. Let's say that I have a periodic signal x of t, okay? X average can be determined by taking our signal, x of t, integrating it over exactly one period, and then dividing by the length of that period. And this is something that I feel like you guys probably should have learned in your calculus classes and all of that kind of stuff. But essentially, if we want to know what the average value is, we take the integral over one period and then divide that result by the length of the period. And that gives us our average value, okay? So coming back to what we were talking about, I could say that my average power absorbed by an arbitrary resistance would be 1 over the period of the integral over one period of whatever my periodic voltage is squared divided by my resistor value. Just using Ohm's law and our fundamental definition for power, okay? So what I can do with these two relationships, and I've described this periodic voltage extremely generally. The only thing we know about V is that it is a periodic signal. We don't know if it's a sine wave, a combination of sine waves, triangle, square, whatever. We don't care except that it's periodic. I can equate these two relationships and try to solve for the DC voltage, which is just the effective value that we're looking for, right? So if I equate these two things, I would have V effective squared, which is taking the place of my DC voltage, since the effective value is just a DC equivalent, divided by my resistance, is equal to 1 over my period times the integral from 0 to t of the square of my periodic voltage signal divided by R, and I'm integrating with respect to time. So it seems fairly obvious that I have a common factor of 1 over R on both sides, so I can literally just get rid of it. So the size of the resistor in this case is completely immaterial, doesn't matter at all. And now I'm left with V effective squared on one side and this mathematical expression on the other side. So it stands to reason that I could pretty easily determine V effective just by taking the square root of both sides. And so that's going to give me the square root of 1 over t times the integral from 0 to t of the square of my voltage with respect to time. And we typically give this effective value for a voltage the units, volts RMS, where RMS stands for root mean squared, and we call it root mean squared voltage because we literally took the square root of the arithmetic mean or the average of the square of the signal that we were interested in. Okay. Following an extremely similar derivation, we could wind up seeing that I effective would be 1 over t times the integral from 0 to t of I squared dt. And our effective value for our current would be in then amps RMS, because once again, we just took the root of the mean of the square of our current waveform. So back in circuits 1, we probably spent some time applying this particular relationship. We can definitely do that again if you guys feel it's necessary, or we can probably just jump into a couple of things, okay? So let's jump into a couple of things here. So some important stuff. So for a single frequency sinusoidal signal, So let's just say that this is x of t is xm cosine omega t plus some generic phase angle theta x. Our effective value would be found by doing the square root of 1 over the period of the integral from 0 to t of the square of this signal, where that's going to look like 1/2 xm squared plus 1/2 xm squared cosine twice omega t plus twice theta x. And this is all taken with respect to time. I could then, for what it's worth, split this integral up into two parts to make it a little less unseemly. So I would have 1 over t times the integral from 0 to t of 1/2 xm squared dt plus the integral from 0 to t of 1/2 xm squared cosine twice omega t plus twice theta x dt, like so. So my question to you all is, what happens when I integrate a sinusoidal function over some integer number of periods? In this case, that integer would be 2, but I don't really want to get into the weeds of why it's 2. Maybe I'll frame the question graphically. So let's say that I have a sinusoidally oscillating signal. I'm just going to assume that my phase angle in this case is going to be, my total phase angle is going to be 0, because I'm bad enough at drawing sine angles that I don't want to make it any, or excuse me, sinusoidal functions that I don't want to make it any harder on myself than I need to. So let's say that we have something like this. So on and so forth. And again, for reasons I don't want to super get in the weeds about figuring out, it's not crazy hard by any stretch. It's just going to take 5 minutes that I don't want to waste our time with. Essentially, what I'm winding up doing here is I'm going to be integrating over 2 cycles of this waveform, okay? So I am essentially adding all of these areas together. So the question that I posed to you a few minutes ago is, what is the area under this curve equal to? And I think now that we've got a graphical representation, it might be a little bit easier for you guys to answer. So any thoughts? It's 0, exactly right. So the area above the horizontal axis is completely canceled out by the area below the horizontal axis. So this whole term right here, the integral from 0 to t of this guy, is literally just going to be 0 because we're integrating over an integer number of periods of our sine wave. So that leaves us with just this rinky-dink thing on the left-hand side, which is actually a constant. So it's pretty easy to figure out what's going on, right? So if I continue on down here, I wind up getting 1 over t. I'm going to pull out that factor of 1/2 xm squared, integrating from 0 to t of dt. Well, the integral from 0 to t of dt is literally just t. So this integral cancels this 1 over t, and it just leaves me with xm divided by the square root of 2. Okay. So for a single frequency sinusoidal signal, the effective value is always just going to be the magnitude of that sinusoid divided by the square root of 2. It doesn't matter if it's a sine function or a cosine function, but we derived it for a cosine function here. It doesn't matter what our angular frequency is. So it doesn't matter if we're here in the United States where our angular frequency is 120 pi radians per second. It doesn't matter if we're in Europe where the angular frequency is 100 pi radians per second. The phase angle that we start our measurement at literally doesn't matter at all. Regardless of where we are in the world, what time we do anything, yada, 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 the effective value of a sinusoid is just the magnitude divided by the square root of 2, which we all should remember from circuits 1. So now let's see if we can wrap our heads around what's going on when we have a multi-frequency circuit. Okay. So I want to scroll back up here, and we're not going to bog ourselves down with doing a bunch of math that we have essentially already done, okay? So if I were to square my voltage, I'd wind up with a result incredibly similar to this, except that all of those IMs would have been replaced by an additional VM, right? We know that the resistor value of interest or whatever would have wound up canceling out. So we would have wound up taking the integral of this giant thing over 2 periods again. And what we would find out is that only our DC terms wind up surviving, exactly like we saw for our single phase system, okay? So essentially, all of those cross frequency terms where I've got omega-2 minus omega-1 or omega-2 plus omega-1 or twice omega-1 or twice omega-2, they all have an average value of 0 if we integrate over exactly 2 periods. And the only thing that survives is what we're left here. So we can generalize this pretty easily, okay? So for a multi-frequency sinusoidal signal of the form where, let's say, x of t is equal to xm1 cosine omega-1t plus theta x1 plus xm2 cosine omega-2t plus theta x2 all the way out to xm sub n cosine omega nt plus theta xn, our effective value, x effective, is going to come out to be the square root of xm1 squared divided by 2 plus xm2 squared divided by 2 all the way out to xmn squared divided by 2. So let's generalize this a little bit more. Okay. So instead of putting it in the terms, or in terms of the magnitudes of each of those portions of the signal, we can actually express this in terms of the effective values of those individual portions. And so what that would look like is it's just going to be the square root of x effective at omega 1 squared plus x effective at omega 2 squared all the way out to x effective at omega n squared. Like so. And I realize it's probably you guys' first time ever seeing something like this, so I do want to provide you with a brief example to show you how to use it, okay? So let me get rid of this stuff right here. So let's say that I have a voltage signal V of t that is of the form 5 plus 8 cosine 50t plus 29 degrees plus 12 sine 100t minus 18 degrees volts. I want us to find the effective value of this guy. Okay. So I know this might seem a little odd because everything that we derived up here said that this is for a multi-frequency sinusoidal signal. And you may argue that the example that I have given you isn't a multi-frequency sinusoidal signal, but I'm creative, okay? So I'm going to say that that DC signal is indeed a sinusoidal signal, but my sinusoid is oscillating at a frequency of 0 radians per second, right? So my question to you all is, what is the effective value of 5? It is indeed 5. So the effective value of a DC signal is just the DC signal. What is the effective value of 8 cosine 50t plus 29 degrees? Why is it taking so long? 8 over square root of 2. It's a sinusoid, isn't it? What is the effective value of 12 sine 100t minus 18 degrees? 12 over the square root of 2. So putting these things together, we could then say that our effective value is going to be simply the square root of 5 squared plus 8 over the square root of 2 squared plus 12 over the square root of 2 squared. And if I throw that into my calculator, nope, I want square root, not cubed root. I wind up getting the square root of 129 volts RMS squared, essentially, because I'm doing everything in effective values, or 11.358 volts RMS. And then once we know this effective value, we can easily use it to calculate our average power, which would just be V effective squared divided by whatever resistance that we were interested in, et cetera, et cetera, et cetera. Okay. All right. Let's set things up for complex power on Wednesday, but not really get into it. Okay. So circling back around to our single phase systems, okay, which is where the bulk of our time is going to be spent. We know that our average power could be expressed as 1/2 Vm Im cosine theta V minus theta I. Okay. Well, I can split that factor of 1/2 up into 1 over the square root of 2 multiplied by 1 over the square root of 2. And then I'm going to distribute those factors of 1/2 as follows. So I could write this as Vm divided by the square root of 2 multiplied by Im divided by the square root of 2 times the cosine of theta V minus theta I, which is the exact same thing as the effective value for our voltage in a single phase AC system multiplied by the effective value of our current in a single phase AC system times the cosine of theta V minus theta I. Okay. Now, what's interesting about this result is that it is the real part of a complex multiplication. So I'm going to set that up really quickly. So this is going to be just kind of a reminder type thing. Okay. So in the time domain, we have a voltage signal Vm cosine omega t plus some phase angle theta V. And current I of t is Im cosine omega t plus theta I. To this point, we have represented these signals in the frequency domain as simple phasors, right? Where we would have a phasor voltage V is Vm angle theta V, and a phasor current I that is Im angle theta I. Well, complex power is based on a slightly different representation, okay? So instead of having this simple V phasor, I'm going to have what's called an RMS phasor voltage that's designated with that tilde over it instead of just the straight bar. And this is just letting me know that I'm using effective values in my phasors now. And similarly, I'm going to have a current phase, that'll be I with a tilde over it. Okay. Well, this RMS phasor voltage is defined to be simply my phasor voltage V divided by the square root of 2. Because if I have a single phase, a single frequency of excitation, the effective value of my sinusoidal voltage is just going to be the magnitude of that guy divided by the square root of 2. And so this is going to look like Vm over root 2 with an angle of theta V, or V effective with an angle of theta V. and my RMS phasor current is going to be the exact same relationship. So I'm going to have my phasor current I divided by √2 is going to look like IM over √2 with an angle of theta I, or simply I effective theta I. And if we come back to our average power relationship, where we had V effective times I effective cosine theta V minus theta I, this can be thought of as simply the real part of me multiplying my RMS phasor voltage V times the complex conjugate of my RMS phasor current I, and we call this product the complex power. This is where we're going to stop for today. We'll get into all of the relationships and nuance of dealing with complex power and stuff in our class meeting on Wednesday.